1.4, the limit of a function. So the notation, the limit as x approaches a of f at x equals L, right? And then this is like some number. This is read by as the limit of f at x as x approaches a equals L. So approaches is that arrow, okay? And then the limit as f at x. So you'd read it, the limit of f at x as x approaches a. Okay, and what this means is that the value of f at a can be made arbitrarily close to L by choosing x sufficiently close to a, but not actually equal to a. Okay, so we've seen this in 1.2 and 1.3, where the number gets closer and closer and closer. We were denoting it by h, so that difference in the h value is infinitely close, but doesn't touch and doesn't equal. Okay, but the limit as x approaches a of f at x exists if and only if the limited value from the left equals the limited value from the right. So I'm going to go over this, what this means both algebraically and graphically. Okay, so here is this as like a formal definition, okay? Limits and their existence. We say that the number L is the limit of a function y equals f at x as x approaches the value of a, written as the limit as x approaches a of f at x equals L if, so here are the conditions, okay, so conditions. The limit on the left-hand side, and this is denoted by this a, so the limit as x approaches a from the left, okay, the limit of f at x as x approaches a from the left equals some number, but that number also has to be the limit of f at x as x approaches a from the right-hand side. So this left-hand side and this right-hand side, very important. If those numbers do not equal the same number, the limit of f at x as x approaches a does not exist. And you can just put does not exist. Okay, so let's go ahead and investigate. Determine the limit of this function here, y equals x squared minus 1 as x approaches 2. So what we want to do is we want to take all of these values that are close to 2. So we're starting at 1, so 1 unit on the left, and then we're going to start 1 unit on the right, and then we're going to get closer and closer to 2, right? So 2.5 would be half unit on the right, 1.5 would be half unit on the left, and this side is coming into the 2. Okay, 1.9, 2.1, these are both 0.1 units away. These are both 0.01 units away, 0.001 units away. We're going to get infinitely closer to 2. So let's go ahead and sub these values in. So for example, 1 squared minus 1, we're going to get 0. 1.5 squared minus 1, we get 1.25. And we're going to go ahead and do this for all of these. So the values that we would get are 2.61, 2.9601, 2.996001. F at 2 is 3, right? 2 squared minus 1, 4 minus 1. Okay, then we get 3.004001, 3.0401, 5.25. I'm missing one value. Oh, 3.41, 5.25, and 8. So what the limit actually means is like we are taking a look at y equals x squared minus 1, and we're going to take a look at how that equation acts as x approaches 2. So this is our value right here. And this value actually at 2 doesn't mean anything when we take a look at limits. Limits just limits just mean like what the graph is approaching. So if we can see a trend in these numbers, 0, 1.25, 2.61, 2.9, 2.99, 3, we can see that as we move in and in and in until f at 2, but again, f at 2 doesn't matter. That's going to come up in continuity, but we are approaching the number 3. Okay, so we can say the limit as x approaches 2 from the negative side of f at x is 3. Okay, so what this number means is our values, or the graph, or the function, whatever you want to call it, because all of these are valid, approaches 3. Okay, and then this is on the left-hand side of 2. On the left side of 2. And when we do the same thing from the right side, when we start at 3 and then we move in and in and in, we start at 8, 5, 3.4, 3.04, 3.004, right? Those values are getting smaller and smaller. There's more and more zeros beside the decimal. So as we go in from the the right-hand side, we're also actually approaching this value here, which is 3. And we can just make a note. So our values, and I'm not going to rewrite all of these again. I'm just going to say approaches 3 on the right side of 2, or x equals 2. So because the limit from the left-hand side and the limit from the right-hand side are the same value, we can say, therefore, since the limit of f at x as x approaches 2 from the negative side equals the limit of f at x as x approaches 2 from the positive side, the limit exists. And we can say the limit as x approaches 2, just in general, of f at x, equals 3. And you notice there's no positive negative on here. Okay, this is just the limit in general at that number, like as x approaches 2. I shouldn't say at that number, as it approaches that number 2. Since it approaches the same number from the left and from the right, which are, again, from up above, this is the condition, then yes, the limit exists and the limit equals 3. So let's go ahead and graph this, okay? And it's just going to be a rough sketch. So if we're talking about x squared minus 1, we go through the vertical axis or the y-axis at -1. Okay, so this is going to be x squared minus 1. Okay, let's call that f at x. Now, for the value of 2, so that would go approximately here, right? And then that would be 3. So this is what happens. What we're looking at is as we go from the left-hand side, what number are we approaching? Well, we're approaching 3. Remember, we always look at what the y's are doing, and then we talk about the x's, like we talk about the domain. Okay, now let's go in from the right-hand side. We also approach 3. So this is all the limit means. The limit just means what number it approaches. And this is going to be the y value. Example 1, use the table of values to evaluate the limit as of the function x squared minus 1 over x minus 1 as x approaches 1. Then graph this function to check. Okay, so from 0 all the way to 0.999, what we're doing is as x approaches 1 from the left-hand side, right? We're coming in from the left, okay? 1 is going to be our number that we're evaluating at, right? The limit as x approaches this value, okay? But again, this value doesn't actually matter, okay? And then we're going to calculate from 1.001 to 2. From this number to this number, and then these numbers were coming in from the right. So let's go ahead and sub these in. The values that we get are 1, 1.5, 1.9, 1.99, and 1.999. Okay, so as we can see, what number do we approach here? If you think about it, f at x equals x squared minus 1 over x minus 1 approaches 2 from, below. I'm going to revisit this, and then from above. Okay, when we sub in 1, what ends up happening to our function? We actually get 0 over 0. This cannot happen. This is called indeterminate. Indeterminate, E-N-T, A-N-T, okay, indeterminate form. We cannot evaluate 0 over 0. Okay, and then coming in from 2, we go from 3 to 2.5 to 2.1 to 2.01 to 2.001. Again, we're getting closer and closer and closer to the number 2. Now, let's actually think about this. Why do we get 0 over 0 in this middle number? So we have f at x equals x squared minus 1 over x minus 1. If we were to factor the numerator, we are going to get x minus 1, x plus 1, and then the denominator will stay the same, x minus 1. So from advanced functions, when we cancel out in a rational function a term in the top and a term in the bottom, and it obviously involves an x value, what ends up happening is there's a hole. So there's going to be a hole at x equals 1. Okay, and then our f at x is going to simply be a line. This is x plus 1. So we went from a rational function, and after simplifying, we realized that this is just a line with a hole in it. So what ends up happening is, if we want to solve for where this hole is, so we know it occurs at x equals 1. So if we sub this in, so f at 1 equals 1 plus 1, which is 2. Our complete coordinate of the hole is going to be 1, 2. So 1, 2, there's going to be a hole. Now, if we're thinking about the function x plus 1, I'm thinking about this coefficient of x is going to be our slope. So our slope is 1. And this number right here is going to be our y-intercept. So our y-intercept is also 1. So if we locate the y-intercept, we can go rise over run, rise over run, rise over run, right? 1 up, 1 over, okay? And then 1 down, 1 over, 1 down, 1 over, 1 down, 1 over, the other way. So this is going to be our function f at x, our simplified function. What ends up happening is, if we can, let's go back and talk about the limit. So we're coming in from the left-hand side. What number do we approach? We approach 2. Now let's come in from the right-hand side. What number do we approach? We also approach 2. Let's put from the left here and the right here. I don't know why I put above and below, but now after this, we can say the limit of f at x as x approaches 1 from the left equals, equals 2. And this also equals the limit of f at x as x approaches 1 from the right-hand side. So because we're coming in from both sides to the same number, the limit exists, and the limit is 2. Example 2, the limit of a piecewise function. So let's determine the limit of f at x as x approaches 1. So this one's a little bit different because we're no longer looking at a single function. We're looking at like a piecewise function. So this function is made up of 3 different functions here. Okay, we have x minus 1, which is, if we think about it, this is linear, right? It's a line. And it's on this certain domain as when x is less than 1. So let's locate 1. And then when x is less than 1, if we think about this, the slope is 1 and the y-intercept is negative 1. That's what we're looking at here. So you plot the y-intercept first, and then we go up 1 over 1. So we are going to have an open circle here because there's no underline here. So this is not an indication about whether or not it hits this 1. It just gets closer and closer and closer to like 1 comma 0. Yeah, 1 comma 0, but doesn't ever hit. Okay, and then we can go down 1, left 1, down 1, left 1. So we pattern backward, and this is going to be our x minus 1. Now, the second part of this, f at x equals 1. If we think about this, this is usually a horizontal line at 1. Here's the difference though. Okay, so it is on the domain as x equals 1. That means it only occurs right at that point. This is going to be a single point, right? Usually it's usually a horizontal line, but because the domain is only 1 point, this is going to be the point 1 comma 1. So we can graph 1 comma 1, and we can circle that in. Okay, and now the third piece of this piecewise function. We have a radical function, and all this is saying right 1 unit. This is saying up 2 units, right? So if we rewrote this as x minus 1 and then plus 2, what we'd have is we would have the point 1 comma 2. And we can read that. Okay, and again, this is on the domain x is greater than 1. So when looking at this domain, there's no underline here, so we're not going to include it. We're going to do an open circle. Okay, so at 1 comma 2, open circle, and then what ends up happening is this is just a radical function. So, and we can label this if we want to. Here we go, f at x equals 1 at that point. Okay, so let's talk about this. This question asks, determine the limit. And that's always dependent on if the limit exists. Okay, so the definition of limit is we have to find the limit as x approaches 1 from the left, okay, of f at x, and we have to find the number, and we have to assess if this is also the limit as x approaches 1 from the right, okay, of f at x. So what we want to do is, because you're not always going to get this like a graph, and it's not always going to be so easily straightforward to graph it. Okay, this is quite straightforward. What's going to happen is we're going to have to take a look at the domain. So when we look at this, like look at the domain, to see the part of the function we work with. Okay, I don't want to say the function because this is actually one function, but it's broken down into 3 because it's a piecewise function. So just the part of the function that we're going to work with. So as x approaches 1 from the negative side, I'm thinking when x is less than 1. So let's go up here. I'm going to locate that. The part of the function that we're dealing with for this one is f at x equals x minus 1. So what we'll do is, and this is just a note, so now what we'll do is the limit as x approaches 1 from the negative side of x minus 1, right? And remember, when we write the limit as x approaches 1 from the negative side, as soon as we sub this in, we drop the limit. So 1 minus 1 equals 0. So we can say the limit as x approaches, this is an arrow, sorry, 1 from the negative side is 0. Now, let's go from the positive side. So when I'm thinking as x approaches 1 from the positive side, I'm thinking when x is greater than 1. Okay, going back up here, x is greater than 1, we're going to deal with this root function here. So f at x is going to equal 2 plus root x minus 1. All right, so let's do the actual limit of this function. So the limit as x approaches 1 from the right-hand side, we're dealing with this function. So as soon as we sub in this 1, we no longer have to write the limit anymore. So 2 plus 1 minus 1. So we're going to get 2 plus root of 0, which goes away, which is just 2. So let's take a look. Is 0 and 2 the same number? No. Going back up to the graph, let's do this in a bright blue. Going up to the graph, as we approach from the left-hand side, we approach the number 0. But as we approach from the right-hand side, we approach the number 2. So because these are not the same number, the limit does not exist. Okay, and we can make a statement here. So the limit as x approaches 1 from the left of f at x does not equal the limit of f at x as x approaches 1 from the right-hand side. Therefore, the limit as x approaches 1 in general, right? No positive or negative signs there, okay, of f at x does not exist. And again, I want to point this out to you. It does not matter what is actually happening at this number. This does not matter for limits. That number can exist, can't exist. That number could be different. It doesn't matter. The limit is just, are we approaching the same number from both sides?